Okay, let's get started. So today I want to talk about the assignments for the class. And then I also want to show you the EMS system. The EMS is not, and I'll talk about that in a few minutes, it's not set up for this class yet. So I have to show you the object-oriented programming in Java EMS entry, which is now working. Earlier when I tried to show it, that wasn't working. So anyway, if you're curious about assignments, you'll see in the bhacker.com website, you'll see a list of assignments for the course. And what you're looking at on the screen right now is assignment number 1. Nothing has been due yet. You haven't missed anything. Nothing will be due until the very last day of the course. So you have now until the next, I don't know, 13 or 14 weeks, I can't remember how many weeks we have left, to do all of the work. So you don't want to wait till the last minute, but for those of you who don't have logins, some people just joined the class today. Some people don't even have logins to the EMS. So I'm not going to hold this against you, and it's kind of hard to set a due date, and then I'm going to have panicking students who can't turn stuff in, essentially. So no due dates. So that's why I have no due dates. But it doesn't mean that nothing is due. So what you're looking at on the screen is assignment number 1, which you can do. Actually, you can't probably work on assignment number 2 yet because I haven't talked about entity relationship diagramming. But that one probably by the end of next week. So what I'm going to do is as we go through the course is talk about the assignments, my expectations for them, how to turn it in as we go through the course. I'm not going to talk about all of the assignments today, just assignment number 1. And then we're going to finish part 2 of the SQL Bootcamp that we started last week. For those of you who were here last week. So that's pretty much the plan or agenda for today. In terms of this first assignment, it's not a tough one. You don't even have to have any experience in databases at all, and you don't need Oracle installed in order to do it. What you're doing is you're going to design a medical records management application, where your coworkers aren't too keen about the idea of using commercial database systems, so you're going to talk them into it. So it seems like a lot of smoke and mirrors. So what you're going to do is you're going to write a convincing proposal memo to your boss explaining the benefits of using a database management system. It's a simple assignment. You can go out on the internet and actually look at information. You're not designing the database. You're not doing anything. You're just writing a summary of some convincing statements if you were to say, hey, this is what we want to do. Putting any format that you want. I would put it into a Microsoft Word file, actually. And when you get done with it, it actually gets uploaded into the ITU EMS system. It gets downloaded from bhacker.com right now because the EMS system is empty. And let me just show you that, actually. I've been logged in under a student for this particular, actually it's not for this class, it was for the object-oriented in Java class. My login actually worked, so if you were here for the earlier class, we had a little issues with that. We weren't able to get this far. Our class will show up, and let me make this a little bigger so you see it. It says Oracle Database Management Administration. It should show up in your courses, so after you get logged in, if you hit My Profile, you should be entered in, and this is not me. So you'll see courses. If you click on the courses link, you see a list of courses that you should be enrolled in, hopefully. If you don't see this, don't panic, but contact the ITU folks. I can't get you logged in, can't fix those problems, can't make these courses available for you. But the ITU folks can do it, and they are still working on getting people logins and getting things set up. In fact, the class, if we hit on Oracle Database Management Administration to go into the class, what we see is some course information at the top, and then you see nothing really at this point. You just see some lecture videos, these videos recordings. This is the video. These links for the video are from this particular camera that's videotaping the screen. And as you know, I also have recording going on the computer that's being put into YouTube. Then those links are from the bhacker.com site. So it's your choice which one you would prefer to look at. They have the same content. They're the same. They're being simultaneously recorded. But sometimes the audio works on here. Sometimes it doesn't work on here, and vice versa. So it's just basically 2 shots. One of them's got to be good enough to actually look at and view. And what we're missing from here, and you can see, it's just a bunch of dates. And there's nothing in here yet, so you haven't missed anything, long story short. So if I zoom out a little bit, it gives you kind of the full picture of it. It's pretty empty. So you can't even submit anything even if you wanted to. So once you're actually able to submit, when the course has been filled out, it'll look more like the object-oriented in Java class. And if you're in that class, here's your picture of this one. The O Design in Java course. Oh, now it's not going to work. It was working a few minutes ago. Oh, here we go. Here we go. So now we have unit learning objectives. It should essentially follow the format of the syllabus. Lecture 1, Lecture 2. Here we go. Assignment number 1. We'll see links that are going to be in a kind of a slightly different unit-by-unit format. You just go through and look for the assignments. You don't actually have to read any of the stuff in here because you've already got it from vhacker.com. You can only, if you want, you could just use this to submit the assignments. Here's another question that students have. When you click on the link to submit the assignment, a couple of things to keep in mind. You have to scroll all the way to the bottom of the, and then you see the browse button where you can upload a file. A few words of caution, because I will guarantee to get at least half of you sending me an email message with one of two problems. First problem, I submitted the wrong file. How do I resubmit it? You can't. I've submitted a change to have that fixed, but currently as to this date, you can only put in one file. You can only put it in one time. So make sure when you're uploading it that you're actually uploading the right file, because otherwise we can get the TAs to remove the file and then you can upload it again, but it's a hassle. You have to contact the TA, and that's my advice. Contact the TA if you've uploaded the wrong file. Another thing is you can only upload one file. Not really a problem for this class, but for the object-oriented programming in Java class where we're writing multiple files, you have to compress them all into one. So just keep that in mind, only one file at a time and only once. So it's kind of restricted. Hopefully that will change in the future. But that's just something to keep in mind. And if you do run into a problem, the TAs can help you out with that. So I know I kind of went through that kind of quickly, but are there any questions that anybody has at this point about uploading assignments? No, some of the returning students are very familiar with this process already. So some of the new ones haven't even gotten a login yet, so they have no idea what to expect. Just remember those two restrictions, though, because that might save you some time. And also remember that we're going to hopefully set the due dates for the very last day of the course. So if my TAs are listening, the very last day of the course is the due dates. Because what ends up happening is if the date expires in the system, you can't upload it anyway. So I have to set the due date as the very last date. Otherwise, people can't turn anything in late. Because then it's blocked. It's restricted. So don't worry about that. We'll make sure you have plenty of time on that due date so you don't run into that problem. That one we can actually fix. So if you do have questions about the EMS or questions about that first assignment, if you've just walked in and missed my little review of it, then feel free to approach me after class, or you can send me an email message and I can explain a little bit further on that. But not technical. You don't have to come up with a diagram or anything. Just create a memo of any format. Put yourself in the shoes of a business person who has to decide, how are you going to convince somebody else that you really want a database? Yeah, my hand does go in there. Okay. All right, so last lecture we were talking about, oops, what's going on here? Autosave. Oh, there we go. Last lecture we were talking about SQL, and I called it SQL Bootcamp, and we actually covered the first part, which was a lot of SQL. If you missed it, there's no help for you. I can help you, but go back and go through the first part of this lecture, especially if you don't have an SQL background. This second part is going to be even more difficult. It's not more difficult. I shouldn't say that, because when I start saying that something is hard, people think that. So it's really easy, actually. So just to refresh your memory on these points, we talked about what SQL was. We looked at the select from where, and some notes for brand new people. We're talking about beers, bars, and drinkers. as the theme of the tables, and the entire lecture set works off of that theme. The basic query of the select a name from beers, where, manufacturer. I put everything on 3 different lines. You can put it all on 1 line if you want. Just remember that as well. I have the keywords in capital letters. Not a bad idea, actually. It's not a bad convention. A lot of people use that because then you can actually point out the keywords, and especially for brand new people who are looking at this, or if you want to make it like extremely easy for people to follow. It's a nice convention to use. Not required. SQL is not case sensitive unless you're doing a comparison with quoted text. Anyway, so we looked at the meaning of a single relation query. We haven't talked about joins yet. What we've talked about is pulling information out of more than one table. A single relation query has one table listed on the from. So here we have a single relation query where we have select star from beers where some condition exists. And the result set that comes back in the form of a table, commonly referred to as a result set. It's really a table, actually. It's a table format. What this happens is if you pull up the SQL window, and next week, probably not next week, the following week, I'll have that SQL Plus window, and I'll show you the queries as we enter them in. But I have to talk about database designs first before I get to that point. So, as a preview, next week is going to be the first lecture, I believe, on entity relationship diagramming, unless I don't finish today. And we'll have SQL again next week. So, renaming attributes. When we do this select name as beers, comma, manufacturer. When we're doing the as, we're actually renaming or creating an alias from the select line, which is different. We're not renaming the column in the database, if you remember that point. And then in the query, we have beer that shows up in the column instead of right here, where the beer that shows up instead of the word name, so we can make the result set more meaningful. Let's see, we had talked about expressions that existed in the select clause, where we can select bar beer price times 120 and go as price in yen. In this particular example, that basically tells us that we can add the alias to make the expression more meaningful in terms of what it's expressing. And in the result set, we see price in yen on the last column. This is review. I've covered all of this stuff already. This is the last lecture. But sometimes it's hard to pick up in the middle of something unless you go back and take a few minutes to review. And then here's a constant expression that we added to the select clause as well. To say as who likes beer, we're adding in the constant expression likes beer, likes bud, excuse me. So we have a new column, who likes bud, with likes bud. We have that because we can run the query a couple of times, and depending upon how we're doing our where, we can actually select the beer is equal to Miller, or the beer is equal to Heineken, or something, and then how do we know what those results are? So this basically self-documents the results by adding a constant expression in the select that appears in the result set. We want that because we're going to take that and use it in an application or something, and then we can take, well, what about, who likes Bud? These people like Bud. Who likes Miller? These people like Miller. And we can basically make the result set more identifiable. And then we also looked at complex conditions in the where clause. The where clause being at the bottom, where we have Joe's bar is equal to Joe's bar and the beer is equal to Bud. So we can compound expressions. Looked at the and, the not, the or, and the different clauses that we can put in there. The concept of the apostrophe as well. The second apostrophe when we want to include an apostrophe in terms of the where clause and the selection criteria. We also actually looked at the concept of patterns because sometimes we want to search on a wildcard, and maybe we want to search on the exchange 555, so we could say anything before it, plus, and then these underscores here. In the where clause, phone is like, similar to like. The constant word is like that we use. The underscores say character, character, character. The percent sign is any. It's like a wild card. It's not the asterisk. A lot of people think it's the asterisk, and they'll put that in there because everywhere else we use an asterisk. It's everything, right? No. That'll give you an error message, actually. The null, the meaning of null, we covered this last time as well in terms of we can compare with null, check for missing values. Why do we need to worry about null? Is because it screws up the logic in terms of is it true or false. If it's null, it's unknown because we don't know if it's true or false. So it's actually a composite of 3 different states that we can test for in terms of the logic. 3-tiered. So in the tier we have true is 1, false is 0, unknown is 1/2. In terms of it's half true, half false, I guess. It's unknown. We don't know, one or the other. Depending upon how you design your query, you might actually end up with different results that come out of it, especially if you're doing a count on something and you have nulls. Is it going to count the nulls? If the condition is true, add 1. It may not if it's unknown. If it's not true, it's unknown. So you have to consider that. We also looked at multiple relation queries. So we had multiple relations, and then if you haven't figured it out yet, a relation is another word for a table in relational database design. So here we have select beers from likes, frequents, 2 different tables. So instead of a single, we have multiples. And the formal semantics of the single relation queries are the multiple is almost the same as the single. And what we're doing is going through different rows. So this is actually, as I mentioned before, kind of time consuming. The more tables we list, the more we select out, the longer it takes for the query to run, actually, because we have to go through every single row in this table, every single row in that table. So there's ways of actually making that more efficient by saying distinct or all, or actually doing a join, which we haven't talked about yet on the tables. I don't think we have talked about joins yet. So sometimes we actually have to make 2 copies of the same table because we're searching the table on the table. Maybe we're looking for someone who meets this condition and they also meet that condition, and they're all coming out of the same table. So the concept of using what's referred to as 2 copies of the same relation, we have select b1.name, b2.name, and it's coming from beers space b1, comma beers space b2. So we're using the table twice with 2 different aliases because the as gives us the alias, and we're querying the table on the table. So, and then we actually started looking at subqueries. This is when most of you started going, oh my god, is there more to this? There is more. Actually, we have more. So the subquery is a query inside of a query. You can subquery anywhere you want, actually. We looked at guaranteeing at least one particular result if you're going to do a comparison. If you're trying to check to see if something is equal to something, your subquery has to come back with only one answer. So it's going to come back with, in this particular example, select the price. If you came back with more than 1 row, the query is going to throw an error because you can't do an equals to more than 1 unless we start using the concepts that we're going to look at in the next part of the slide set, which we haven't gotten to yet. So in this particular set, so what we've covered so far, we have to know whether or not we're looking at a group or whether or not we're looking at a single comparison. In the in operator, then we can actually start looking at the group and say, instead of something as being equal, and what I'm looking at here is down here, price is equal to, that subquery has to come back with 1 price. If we don't want to do that, we want to make things a little bit more flexible for ourselves. We can say where name is in. Now we're looking at set theory. And so we can actually start saying, well, select beer from lights where drinkers equal to Fred. We might come back with more than 1 beer. So if the name is in that particular set, then it can actually do a comparison with a true or a false, or an unknown, actually, depending upon what we come back with on that subquery. We could create a bad subquery, actually, and it could come back with the wrong names, I guess, theoretically. We also looked at the exists and then the not exists, in terms of whether one relation is true, if and only if the relation is not empty, does it exist? One instance of something in another group. And here's the example of that I went through. Select name from beers B1 where not exists. When it's not in, this is going to find us unique names, essentially, because it's going to be here, but it's not going to be in here, then give it. Because whatever we have on the select line is what we're going to get out of the query in the long run. So keep that in mind. Let's see, we looked at the any as well. We covered a lot last time. So we said x is equal to any relation is Boolean condition where the meaning of x equals at least 1 row in the relation. Does it match any of them? So, or how about does it match all? Or does it not equal to all of them? So the logic in here says what we're looking at is the price from the outer cells that must not be less than any price on the inner cells. So we're finding out where price is larger than or equal to all of the select price from sales. So essentially we're selecting a price from basically using the same database cells twice and comparing one price with all of the other prices that are coming out of it. So now this is pretty much where we stopped, I think. Really close to where we stopped, I believe. And we started looking at relations as bags, grouping, and aggregates, which we haven't looked at, and then DDL, database definition language, or modification, because what we've been looking at so far is manipulation, or DML in terms of the terminology. So I'm going to actually start here because I know I went a couple more slides into this, but this is really a good starting point. So union, intersect, and difference. So we can say, and this is where we start looking at subqueries, because most of you in the first class said, subqueries? I'm never going to use a subquery. Because remember I said you can actually take those subqueries sometimes, make things slower for yourself, run the subquery first, take the value, manually insert it in to the big query, and you can run them multiple times. And it basically creates more work for yourself, but it actually makes it easier to look at. That's all fine and dandy unless you're working with sets. In that case, you can't really do it. So if you have the subquery concept down and you can do it comfortably, then you can graduate on the logic and move forward into this whole brand new set of groups and sets. So union, intercept, and difference, where we take a relation and we cross it with another relation. So we say a subquery union another subquery. So we're going to get this one and this one if the item is in both of the sets together, or if it's in one. Oh no, excuse me, union is going to be in both. If it's going to be the cross-section, the intersection of it's in both, and then the except, it's in one or the other, essentially. And you can't do that unless you have a subquery against a subquery. So let's look at an example here from some from the relations likes, which has drinker and beer, and from the relation sells. We have two relations we're going to cross that has bar, beer, and price, and from frequents, three relations. We have drinker and bar. Find the drinkers and the beer such that the drinker likes the beer, and the drinker frequents at least one bar that sells the beer. And I believe this is the query we stopped on last time, if I remember this right. So we have select star from likes, and then I pointed out earlier that I said we could use these brackets anytime that we want. We don't have to use them up until this point. At this point, we need to start using the brackets because we don't know what we're going to intercept. So it makes it easier. It's actually not technically required, although this is a lot easier to read, in my opinion, because we've got one inside of brackets, kind of small. If it were bigger, it'd be a little bit more difficult, intercepted by another query. And so what ends up happening is the inner query, in fact, in this particular one, both queries are probably going to go one after the other. It doesn't really matter which subquery gets executed first. The final outer query is the intercept. So intercept actually is the highest level, I would say, if you look at the abstract or the hierarchy of what's going on here. So the drinker that frequents a bar that sells the beer is going to be under here. It's going to be intersected with everybody who likes, from likes, essentially the table. So, and we can't just simply put, I've had students write this before, or just put a table name, intercept another table name. It doesn't work. We actually have to run a query on the table. In this case, we can't just say likes, intercept with this query, which would actually, in my opinion, make actually most sense. Why would you run select star from likes? Well, the case being, what if you don't want to select star? What if you want to select something specific? Then this is actually more flexible than just saying a table, intercept another table, which is not legally possible anyway. So bag semantics. So what we have here is a select from where, although that uses a bag semantics, the default for union, intercept, and difference is set semantics. So we've seen before, this is like, what do they call it, discrete algebra or something, or mathematics, in which you're looking at set theories, essentially. So duplicates are eliminated as the operation is applied in terms of the set. So when we get a set, in this case, when we're intercepting, we're not looking at all the duplicates. Instead, what we're looking at is, a more efficient way in terms of the way the query is implemented. So actually, going back to this query for a second, if you think about developing the database yourself, which hopefully some of you could actually do at this point, you have to imagine there's many different ways of setting up the logic. Because you probably would put it into a tree structure, perhaps, because it makes it easier in terms of searching and sorting. And you could probably design that to make some shortcuts, like remove the duplicates, or, especially if the duplicates aren't part of the logic. We have some databases that actually do that behind the scenes, and we have some that don't. And this is where we get separation between the different qualities of databases that are on the market. There's no requirement that they make this efficient, but some languages are naturally more efficient than others. MySQL is very efficient. Oracle is actually very efficient. They both actually kind of follow, although one's an open source and one's a private database. It's hard to tell what the private database is actually doing in terms of their algorithms. I would actually have to assume it's something very similar, because if you ran that same query across the board and did it with Microsoft Access, that would take, Access would probably not even be able to handle it within a day, I think. I mean, Access would be very slow because it's not going to implement any sophisticated data structure or use any kind of memory management organization to optimize that query, essentially. So we have a motivation for efficiency when you write queries, because long story short, the more you query, the more sub-queries you put in the query, the slower the query takes. You write an application. All of our applications these days work on the internet. You have a web page up there. A customer's waiting for the results to come back from a query, a connection to a database. Are they going to wait for more than 2 or 3 seconds? Minutes? And then you got to worry about the user interface. Okay, let's put a status bar. Progress. We're moving. We're going. We're going. Otherwise, users are going to close the screen and go to another website or something. They're not going to sit there and wait. So efficiency is almost the #1 priority when designing queries. And as we've seen, we have many different options, so depending upon which options you select, your query may or may not necessarily be the most efficient. The worst thing you can do is go row by row in every table that you select. That's not a good thing. So when you project on the relational algebra itself, it's easier to avoid eliminating duplicates and just work at a row at a time. Not good, not very efficient. When doing an intersect or difference, it's most efficient to sort the relations first. You can actually sort the relations in an order, because if you think about the concept as I mentioned before, the subqueries are executed first. Then the outer intercept is done when I talked about abstraction. So you have the subqueries always go first. So if you sort it, everyone knows if it's a sorted list, it's going to actually, actually compare easier. It's going to be easier to work with. What about eliminating duplicates? That's not a bad idea. Either you make the result set smaller. So when doing it, if you sort it first at this point, you want to eliminate all the duplicates as well. So in terms of some of the things you can do to control the duplicates, which is going to be a huge cost savings, is force the results to be of a set using a unique set using the word distinct. So the distinct keyword gives you only one occurrence of each row that comes back. Because if you're doing a set, why do you need multiple? You just need one in the set, especially if you're doing this type of a query. You can also force the results to be a bag without eliminating any of the duplicates by using an all, as in union all. Why do you want that? Well, you probably, if you're looking at a cheap and easy join, you want a union all, because you're joining 2 tables together. You're not using a join, you're using a union, which is actually kind of the slower way of doing it. But in some cases, it might be a subquery that you're unioning with another subquery. So it's only a portion of the table. When you do a join, that operation is going to take every single row in this table and join it with every single row in that table. Slower in concept, depending upon the size of the table. So sometimes it makes more sense to do a union all to mimic a join in some of those cases. So that's just one example. When I talk about joins, I'll talk about some more examples. Here's an example of the distinct, where in our query we are finding all the different beers charged, different prices charged for beer. So we have select distinct price from sales. So we have price 1, price 2, price 3. It's a small table, but we're noticing without the distinct we can actually get multiple prices. This might actually be another thing that you might want to watch out for in terms of, because you're building an application as a front end, let's say, and you're running a query on a database that's going to return the results to the front end and use it to populate, let's say, a table or a list. How many times have you gone to a website and you've seen the same item twice in the list? And you're going, well, why is that listed twice? Well, because that's what happened. They didn't do it distinct. Instead, they got all of the ones that came out when they did the query. So you see book one, book one, book one, book one. How many times do you want to see this book? You know, so sometimes it can actually clean up the user interface by using a cleaner result set that's coming back in. Less work. So the point I'm trying to make is either you put the work up here or you put it back here. So the better sophisticated the query, the easier it is to use your results, the less work you have to do on the user front end. And you know that old saying, every bad application can be fixed with SQL? You can actually use SQL to fix a bad table design as well. We haven't talked about designs yet, but you can have an extremely bad, practically non-functioning database and actually get some valuable information out of it by designing the correct queries that work with it. So, but it's a lot more work. Create the database once, you query forever, so it's better to build a better database. So your queries are easier. Here's an example of the all. Using the relation frequents, where we have drinker and bar, and using the relation likes, where we have drinker and beer. We're going to select drinker from frequents, except all, where we're getting the cross-intercept of select drinker from likes. So list the drinkers who frequent more bars than they like beers, and does so as many times as the difference of those counts. It's kind of a tongue twister, but the logic actually kind of gives you a sophisticated result. Did you have a question? Oh, okay, I'm sorry. I thought I saw a hand. Rarely do I see hands, but I am looking for them. And feel free to interrupt me and ask a question if something doesn't make sense, because otherwise I just go on until the time's up, and then they throw the hook out and take me off. So, if you haven't seen the Gong Show, you guys know what the Gong Show is? No. In the old days, you had American television. They had a TV show called The Gong Show. It's kind of like American Idol. No. Yeah, amateurs. I shouldn't say American Idols. America's Got Talent, maybe? I don't know. Yeah, amateurs, they go out and they do their thing, right? If they were really bad, this big old hook would come out and grab them and throw them off the stage. That's what I was making a reference to. I said, until the hook comes out and gets me. But it's a Gong Show reference. But yes. All right. So either I'm dating myself or I'm dating, or I'm working with the wrong demographics. I don't know. Probably both, actually, at this point. So, all right, good segue. Now let's see. Now you're all like thinking, okay, I can handle this SQL stuff. Now you're all relaxed. You're thinking clearer now. Joins. The join expression. Why do students not like join? I don't know. Every time you say join the table, they go, oh my god. Oh my god, okay, could I not join the table? Can we just do something else? Joining is not that hard. It provides the ability of taking two tables and putting them together. That's all a join is doing. Here's the problem with joins. You got table A, you got table B. It's hard to take table A and match it to table B unless you got the identical number of rows. How often do you have the same number of rows in A as you have in B? You're going to get different results if you take A and join it with B than if you take B and join it with A. So the order that you're joining the tables with. And then are you just going to join it? You know, one row to one row? Can you actually say that this row is going to match? So what about your selection criteria? What are you going to join it on? What if you got two tables that don't have primary keys? So you might actually have duplicate rows. So this table A might have a row that matches up with 5 different rows in table B. So you're going to have 5 different rows now in your final result, or do you just want 1 row in your final result? And which one do you select? So we have outer, we have inner, we have cross, and we have union joins, where we can take and cross 2 tables, get the difference. We can take and join 2 tables on each one and include an empty row space for the non-matching joins. Or we can take the inner, connect one with this one, or as I originally started out with, take A and connect it with B, or take B and connect it with A, vice versa. And then we get inners and outers, and people get confused. But it's actually not that bad. Just know that those are all of the selections you have. There aren't any other selections outside of that. The easiest thing, actually, is to take 2 tables, compare an equal field that's in both tables, hopefully a primary key if you got it. That's the best situation. And say, well, where this primary key from this table equals this primary key from this table, and join them together on the keys. That's the easiest thing to do and the most reliable, actually. So let's see what the slide says. SQL provides a number of expression forms that act like a variety of different joins. So let's not look at the word join at this point. Let's just look at the logic associated with joins. So we're going to use bag semantics, not set semantics. So we're not taking the set anymore. We're going to use the bag on it because we get more reliable results. If you're not familiar, the set is equal, one distinct one. Bag is everything, all put together in terms of what we've been comparing. So these expressions can be standalone queries, or they can be used in place of relations in the from clause. Don't let that bother you. So we have product and natural joins by concept. The natural join is R natural join S. Depending upon the SQL version you're using, depending upon the manufacturer of the database that you're talking to, you could have different keywords when it comes to join. This is the other problem. Students don't like joins because they can't figure out how they're supposed to write the query. Because they do it in Access, they use the word join. When they use it in this language, they don't use the word join. Or they use, in this case, natural join or cross join, which is not actually supported on Oracle. So what ends up happening is you have to learn the concepts and then figure out how the SQL version that you're working with is dealing with it in terms of the interface. Sometimes they actually have different keywords. The concepts are all the same. There's only so many different ways you can join a table. So let's look at an example. Likes natural joins serves. So we have the likes table that we're natural joining to the serves. And I think I misspoke actually. I think the word join is supported. I don't believe natural is on an Oracle SQL Plus interface. However, you can buy extensions actually that change, that add, and depending upon what engine you're working with, if you're working with a report generator, sometimes they add their own keywords as well that you can use in the queries that work. So the basics are all the same, but the words sometimes change, is my point. So relations can be parameterized as subqueries, sub-expressions as well. So the theta join. So we have R joins S on a condition. This is more natural. This gets you better results. So you take you take R, you join it with S on a particular condition. When this field in this table equals this field in this table, join the two tables. So that way you get matching information that you can actually use. Can't necessarily be used for accounts because you're going to get different results depending upon what field or what condition you're joining it on. So the results might vary. So as an example, using the drinkers that has name and address as two fields, and frequents, where we have drinker and we have bar, where drinkers join frequents on name is equal to drinker. So we have, because we have two different tables with two different names with two different name fields inside that we're joining, we don't actually have to provide the dot notation where we go beers B1, beers B2, and reference to resolve the where these particular fields are located. We can just actually just say name is equal to drinker. So it gives us all the DA/DB quadruplets such that drinker lives at address A and frequents at bar B. So in terms of that particular example. Outer joins, and don't pay attention right now because I have some better examples coming up with the exact SQL queries. Right now I'm trying to give you the concepts. So I had the theta join. The outer joins, R outer join S is the core on the outer join expression. So optional natural in front of the outer. So we have the left that pads the right or the right that pads the left. And when we talk about padding, what we're looking at is filling in blank spaces where we don't have an entry because we have 20 in this one, we have 22 in this one, we have 2 rows left over. If we join it this way, well, this one to this one, we end up with 20 rows. This one to this one, we end up with 22 rows. You know, so basically, how are you going to resolve the difference? Gives you the outer or the inner. Aggregates. We can join, actually, this lecture doesn't actually have, well, it's coming up, it's mixed in. I don't have any separate joins because the join, in fact, I have another lecture in which I'm going to show you all of the different joins for Oracle. Because this lecture is on SQL in a generic sense, it's not going to give you the syntax, is what the problem is. So let's move on to another concept. So don't fear the joins, and I'll give you some more examples in a future lecture, actually. because you actually have to have data in order to actually see the joins work correctly. Otherwise, it makes no sense to actually put it into perspective. So let's talk about aggregations for a few minutes. We all are familiar with the concept of the aggregate. We have the sum, the average, the count, the minimum, the maximum. We can apply it to the select column, and we can come back with one number. Give me the total number of students registered at I2. It come back with a number that says something. We can also do a count. Count on a field or count on an asterisk counts the number of rows. So here's some examples on the aggregations. From sales, where we have bar, beer, and price. Find the average price of bud. So we have select average price. And again, the AVG, great, works in Oracle actually. May not necessarily work. We have another aggregate function that might be called average, all spelt out. Or maybe it's a different abbreviation that might work in a different dialect, depending upon the database manufacturer. So when it comes to the joins, when it comes to the aggregations, some of the functions, because these are really functions that you're running, may vary in name. But the concept's all the same. So select the average price from sales where the beer is equal to bud. Makes sense. Eliminate the duplicates in the aggregate. Not bad, especially when you're doing a count. You want to have how many beers do we have at Joe's Bar? How many different beers does he sell? Well, the table might have more than one entry for bud, so it might have different variations. So we can get a more accurate count. In this particular example, we have a distinct inside of the aggregate itself, inside of the clause. It's going to basically eliminate the duplicates, so we have distinct price, which means select only one of each one of the prices and count that. We do that instead of counting the entire number of rows, because then, we easily in the sales database, sales table, where the beer is equal to bud, I'm sure, but there might be like Bud Light, Bud, Bud Amber, Bud something else, I don't know, different variations of Bud that might exist, but we can get the distinct that way. So the nulls are ignored in the aggregates. So if we have something that doesn't have a price on it, it doesn't get counted. So that's one of the interesting tricks with count, which is why people like to go count with an asterisk in the middle. Just count everything. Just count the number of rows. Then you've overestimated. Your count is going to be bigger. If you have nulls, they don't get counted. So null never attributes to a sum, an average, a count, because how's it going to attribute to a sum? It's not going to work at all. And it can never be a minimum or a maximum of value used in a column, because it's nothing, it's empty. But if there are no non-null values in the column, then the result aggregate is null. Comes back null as an answer. So here's an example of the effect of the nulls. Select count asterisk from cells where the beer is equal to bud, or select count price from sales. This is what I was trying to show you, but this is the query actually that describes what I was saying. The number of bars that sell bud, the number of bars that sell bud at a known price. So what if they've left out the price? You're going to get two different numbers. And the nulls actually propose the problem that exists in most bad counts. When the count is not accurate, because you can actually count the number of students that attend I2 and get different counts. How can there be different numbers that come out of that? Because it depends on what you're counting. And what if that entry is missing? Or what if the entry is null? What if you counted all the students based on their student ID and some students haven't been issued IDs yet? Then you're going to have a different count. Long story short. So grouping. So you may also follow the select from where with a group by. Uh-oh, you thought you were done. Select from where is a good starting point. Where we have having, group by, a bunch of other stuff. So the expression by the group by and list all of the attributes. So if you're going to group it by something, you actually have to put an aggregate in the select. And I'll get to that in a few minutes. The relation that results from the select from where is grouped according to the values that are in the attribute for the group by. And any aggregate is applied only within each group. So here we have from sales. The sales table has bar, beers, and price. Find the average price for each beer. So we have select bar, comma, average price. So it's going to get Joe's Bar, $5. Larry's Bar, some dollar value. From sales group by beer. So the beers are going to go first, the average price is going to go second. We have the aggregate up here. If we don't have the aggregate up here, we're going to get an error because it's not going to know how to group by. So that actually poses a problem. So here's another example where we have a computed group by. So we're going to compute the drinker bar price of Bud, rows first, then group by drinker. So from sales and frequents, we have two tables. Find each drinker the average price of Bud at the bars they frequent. So we have the subquery in a kind of a green color here. From frequents, this is where we're coming up with our computation. We're selecting drinker, comma, average price. From frequents, comma, sales, where the beer is equal to Bud and frequent.bar is equal to sale.bar. What are we doing there? We're joining the table, actually. So you see joins all over the place, actually. Every time we use more than one table, we can actually do an instant, like not really a join. Unfortunately, that join operation, depending upon how it's supported, is costly. You know, it's not quite as efficient as some of these other methods. So people try to avoid joins in general, actually. Not to discourage you even more from using the join concept, but not only is it difficult to understand, but people just don't like it in general. So here we are grouping by drinker, so we're going to have drinker average price, depending upon who it is. So we can restrict on the restriction on the select list with the aggregation. So if an aggregation is used, then each element of the select list must be either an aggregate or an attribute of the group by. So we have an illegal query example, and the font looks kind of funny on this one. So it means don't write it this way. It's not, I don't know if you can write it. It's hard to write this script stuff anyway. So you might think that you can find the bar that sells Bud the cheapest, because you know you're interested in saving money on your Bud. Select bar, comma, minimum price from sales where the beer is equal to Bud. But the query is illegal, and it's illegal because bar is neither an aggregate nor a group by. So you have to fix the query by adding a group by, actually, on the bottom. You can't leave the group by out. I have, actually not at this school, but at another school, oh, I won't mention, well, Cal State East Bay, I put something like this on a test, and I said, I just gave them the words, and I said, create the query. 90% of them left out the group by, because they don't think, you know, group by is optional. You know, let's just group it by this. But the problem is the query won't work, because it doesn't know what the logic of the query is incomplete, essentially, is what happens. So. Having clause. So the having, and everyone likes having. Having may follow a group by, and they can be, and they should be used together. So this is the other thing. So they'll use a having or they use a group by, but they won't put them together for some reason. I'm not quite sure why. So if so, the condition applies to each group, and the groups not satisfying the condition are eliminated. So requirements of the having condition. The conditions may refer to any relation or row variable in the from clause. It doesn't have to be the same as the group, actually. And they may refer to attributes of those relations as long as the attributes make sense within the group. It is either a grouping attribute or it's an aggregate. So it's aggregated or it's a grouping. So here, let's take a look at an example for the having. And let's look at the logic first, because this one actually makes more sense if you consider the logic. Because that's what ends up with the having. People forget about the having because they can't put the query together, because it doesn't work without the having. So from sales, we have bar, beer, and price. And from beers, where we have name and manufacturer, find the average price of those beers that are either served in at least 3 bars or are manufactured by Pete's. Pete's makes beer. Oh no. So the count is where we're doing the having. So here's the solution. And this is probably, if you can handle this query, you can handle almost anything, actually, in terms of using. Actually, we have group by in here too. We have everything in this query. We have a subquery, we have group by, we have everything but a join. Add a join to it, and then you probably have the most difficult query out there. So here we have beer groups with at least 3 non-null beer bars, and also beer groups where the manufacturer is Pete's. That's the having clause here. So we have the having count bar, because we're not looking for the nulls. We don't want to count the nulls. Larger than or equal to 3, or the beer is in, and here's the beer is manufactured by Pete's. So in order to actually satisfy both conditions, we have to use the having, essentially. The rest of the query is kind of trivial, because we're selecting beer with the average price from sales grouped by beer. But we're trying to take advantage of the conditions. So here's what ends up happening. When you actually have an aggregate and you need to explain what the aggregate means, you use the group by. When you have a condition that you want to apply to the aggregate and the group, then you use the having. So it gives you, having this particular condition, group it by this, give me the average price. If you think of it backwards. Actually, I almost have to start with the way this is written and think of the inner query and then go out with it. But the only problem is you're not given this. You're just given the description. So that's when you always actually look at this description and go, well, what would I have to look at here? I have to look at served at least 3 bars. Or are manufactured by Pete's. But this is actually quite typical what you get of a normal query. Because, you might think, oh, they're just trying to make this hard. What ends up happening is you have to write this application. You're like, hey, give me all of the new books by this particular author who has not been purchased by this particular consumer and is a member of that particular group, that category, because we want to make sure it's a computer science group, because maybe that author does many different groups. Put it all together so you can tell this, thank you, Barbara, for coming back to my website. Last time you purchased it. Now we have this new version available from so-and-so, and it's on this. So how are you going to get the condition of the topic of the book, the author of the book, the user? All this stuff has to be put together. You're going to use having. You're going to use having for that query, which is quite typical, actually, of a lot of web applications that are putting together information based upon user preferences or based upon things that they want to cross-sell or upsell to users. So that's pretty much it in terms of the data manipulation language. For your SQL Bootcamp. That's a lot, but it's everything I ever wanted to know and every query possible. I haven't talked about the join options in terms of the syntax, and that will come at a later date because we really want to see. I really want to show you that with tables that are actually populated with data, so we can see the effects. But take a look at the database manipulation language. That's basically what we're looking at. Now we have the database definition language, where we're defining the tables. Everything you can do with the database can be done through SQL. So most people at this point go, oh, I'm going to use the GUI for that. What if you don't have a GUI for that? What if you're working on a database that's in Texas and you're in California and you're using a remote login and you're entering into an SQL screen where you can type in SQL statements? How are you going to clean the table out? Or drop the table, or how are you going to, you probably don't know drop yet, truncate, or okay, how are you going to add a column to the table, or check for a value on a table, or just do something in terms of the structure of the table, or even create the table. What if you're in California and the guys who are in Texas lost the power, they bought a brand new server and installed a fresh install of Oracle? Hey, can you rebuild this stuff? Are you going to get on a plane and fly out and do it? Nah, you're just going to log in remotely, run the whole script, rebuilds everything all in 5 minutes. And no commuting necessary. So that actually comes in handy. So if you can write SQL to define the tables and the structure, what you end up having are a couple of files, kind of like a program. The files build the tables, set the default information, set the keys, set the primary key, the secondary, do everything. So that if you need to restore the system, you can do it like in seconds. You just run the script, builds everything. Right? So that's basically why this is so powerful. It's used a lot by DBAs. So the modification commands does not return a result. So what we saw before was a result set, which comes out of a data manipulation. Because we're manipulating the data, we're looking for information. Now we're returning with, okay, so we're not running a query that's going to give us anything. So we don't have select from where. We have different syntax that we use for this entire different set. And what we're looking at are 3 different kinds of modifications. We're looking at an insert, a delete, and an update. Update is a change. So we can't say change, we have to update. We're going to either insert or create. Well, we haven't created yet, but let's take a look at it, the insert, in terms of the table. So we have a table that is created, and there's a create table command that actually creates it. I'll talk about that in a few. In terms of the insertion, so to insert a single row into a query, what do we want to do that? Well, we're running a script on a website. So-and-so Barbara has bought another book, and she's filling out the shopping cart, and she's got the form all filled out. Now we got to take all this information, put it in the database, right? Because we always have databases that are running as backends. So we create one query, we send it to the database, and it comes back with a failed or worked. Success or failure is what it comes back. We're not getting anything back. Easiest query to run because it can go and it can be archived, it can be saved, it can be housed for later updates. It doesn't actually have to happen immediately. That's why shopping carts is that runs quickly. Instantly. It just sends it away. As long as it was sent correctly, everything else can continue because we know it's going to be updated, hopefully, eventually. We're not really looking at the time consumption of that query as we do when we're retrieving information. So here's an example. We're going to add to the likes table where we have drinker, comma, beer, the fact that Sally likes Bud. So we're going to insert into, and then insert into is in capital letters because that's the syntax that we're using as the key statement. And the table name is likes values Sally, comma, Bud. If we do this method, it's kind of easy. Only problem is we have to know the order. We have to know that in this particular table, drinker comes first and beer comes second. And you're probably wondering, well, I think I said on day one there's no order. We don't know what order. For the data manipulation, we don't know the order. For the definition, we know the order because we used create table, table name, this column, this column. The same way that the table was created, unless you specify it, is the default order that you're using for an insert. That actually causes problems because then you have, Sally and Bud switched or something, and then you're trying to put the wrong data into the wrong column. It might become a problem. So you can specify the attributes and not have to worry about it because who's going to go around memorizing the order in which you've created every one of the tables or looking at extensive documentation. More commonly, you'll see the table name first, and then you'll say, put this value in for this particular column because this is the one we want. And maybe you're not actually putting all of them in. If you use this method, if you're inserting, you actually have to insert everything. If you leave something out, you're going to get a null value. You're going to get an error, especially if the table won't allow you to put in a null value. Here, you don't have to put everything in. So you may be added to a relation name, a list of the attributes. There are two reasons why you want to do this. So we forget the standard order, as I mentioned before, or you don't have values for the attributes, and you want to put nulls in, and you don't have a system for filling in information or components. And sometimes, actually, the system, if it says null is acceptable, it'll put a null value in there for you automatically, rather than you having to put blanks in. So let's specify some attributes. So another way to create the same identical query is to say that Sally likes Bud, add that to the likes table. We have insert into likes, and then now we're specifying beer, comma, drinker. We can do it in the other order. Doesn't matter what order we put this in. But this matters. The values that we're putting in have to match the same order that we specified. So we've left out maybe another column that existed that we didn't have a value for. So hopefully that'll be empty. Maybe not. Maybe it'll say null. We don't know. We're not gonna worry about it at this point. Kind of allows you to create some really bad designs, which is why people put the constraints on the tables to say not null, or can be null, or must have a value, or put in a default value if nothing exists, because we don't want to leave it empty. So when we join the tables together, we're going to have a problem or something, So inserting many rows. This you'll see a lot because people like to populate data, especially if you've done a dump. Let's say you've taken data from an Excel spreadsheet. You want to put it into a database. And you've got all the data. It's all sorted already. Then you write a little query that takes the data row by row, line by line, and inserts it into the database. Why do it manually? You can just dump it out and put it in. So you may want to insert the entire results of a query into a relation as well. If you want to take it from a relation, put it into another relation. Happens, actually, when you want to recreate a table and you want to populate it from an old table and you want to destroy the old table. You take all that information, run a query on it, only on the good stuff that you want. Take the query results and populate it into a fresh table, brand new table. So it's good, comes in handy. So you can insert into a relation a subquery. So here's an example. You can insert into a subquery. So now we can use a subquery. So we're going to use frequents, using frequents, drinker, comma, bar. Enter into the new relation, pot buddies, potential buddies, potential buddies. I had to remember that one. Name all of Sally's potential buddies. Oh, it's written right there. Potential buddies those drinkers who frequent at least one bar that Sally also frequents. So she can meet some potential buddies for her database. Here we go. Here's the solution where we've got insert into potential buddies, a subquery, and the subquery says select d2.drinker from frequents d1, frequents d2, same table. We're referencing it twice, where drinker d1.drinker is equal to Sally and d2.drinker is not equal to Sally, and d1.drinker is equal to d2.bar. Excuse me, the bars are equal to the same bar. So all the drinkers that go to the same bar that aren't Sally can be her potential friends, essentially. So, and so this pairs drinkers from the rows. So first checking to see if it's Sally. So that's a classic example of how you can do a query from a subquery and insert it into another table. You're using the insert into potential buddies. Delete. Delete's an interesting one, kind of a scary command as well. Because if you say delete space a table name, you've deleted all entries in the table. But then there's this thing called rollback that you can use. So one of the most beautiful things about the SQL Plus window is that unless you've done a commit and you've actually typed in the word commit, nothing has been saved to the database. So you can always type in the word rollback and undo what you just did. Because if you actually kind of quick and you write delete, table name, well, it's all gone. So you might want to come back and undelete it. And you undelete it by doing a rollback. It takes you back, hopefully, and undoes it. So here we have a delete from relation where condition exists. And actually that happens when you accidentally put the semicolon at the end, thinking you're going to make a multiple line query. I actually done it myself, accidentally. And I go, wait, delete table, it deletes everything. It doesn't actually delete the table, it just deletes all the rows in it. So delete from likes drinker, comma, beer. The fact that Sally likes beer, she doesn't like beer anymore. Bud, she doesn't like Bud anymore. So we're going to delete that from the likes table. So delete from likes where drinker is equal to Sally and beer is equal to Bud. And so we have deleted just that one column. We can delete all rows if we say make the relation empty by going delete from likes, where nowhere, delete everything. So that's the dangerous one. Actually, truncate's even more dangerous, but we haven't gotten there yet. Or drop's not bad, truncate's bad. Truncate drops the table without saving the rollback information. Because if you think about what happens when you delete something, let's say you accidentally deleted a huge table, millions and millions of, everyone who's ever bought a book at Barnes & Noble, you've deleted the table. Whoa, that's a lot of rollback information saved. That environment could actually fill up, and you might not have any room left in memory to process anything out until you run a commit. When you run a commit, that command actually takes the memory, makes it permanent, gets rid of the buffered information. In the meantime, everything's buffered, which is fantastic, because you can always go back and roll it back. There are certain commands that don't create buffered information. Truncate's one of them, and I'll talk about it more when I talk about the command, but that's a dangerous command to use. Also, drop is bad, but drop saves rollback information, so you can actually undo the drop. You can't undo the truncate. Truncate's nasty. All right, so deleting many rows, deleting from beers. We have name and manufacturer, all of the beers for which there is another beer by the same manufacturer. Delete from beers B, where exists, subquery. So the subquery is going to give us the beers with the same manufacturer and a different name from the name the beer represented in row B. So it's a tongue twister again. So the semantics of the delete, because you're probably wondering, how does it do a delete then? Well, it's going to take the subquery first and then apply that condition to the where exists from the main query. So suppose Anheuser-Busch makes only Bud and Bud Light. Suppose we come to a row B for Bud first. The subquery is not empty because of Bud Light row, so we delete Bud. Now when B is in the row of the Bud Light, do we delete that row too? So you can actually sort. You can do all other things before you do the delete to get the logic correct. So the answer is that we do delete the Bud Light as well because it's going to exist in the query. So the reason that that the deletion proceeds in two different stages, marks all of the rows first from the where condition and satisfies the original, and then it deletes the marked rows. So it's marking the rows, figuring out the logic, then performing the delete last. So the delete always actually gets performed last after the marking and the changes have occurred. So if we're not going to insert, we're not going to delete, the next option we have is to update. Update is to change. There's no change command. It's always called update. You can actually update and do, no, you can't update and do an insert. You have to use an insert in Oracle. In the old days, you used to be able to do an update, and then if the row didn't exist, it would do an insert for you. Now it doesn't work that way. Now the update is strictly an update. The row has to exist before you can actually insert it. So people would normally do a check on it and say, well, are you there? If you're not there, insert you. If you are there, update you. So you have two queries that have to run with a check. So to change certain attributes, you can update everything or you can update just one attribute, so you don't have to update the whole thing. Update a relation. Set a list of attribute assignments where a condition on the rows exists. Well, it's going to be where you found the right row, hopefully. So here's the update. We're going to change drinker Fred's phone number to 555-1212. I think that's area code information or something. I don't know what that is. Yeah, I think it's information. Update drinker, set phone is equal to 555-1202, where name is equal to Fred. This is where you can come into major problems if you leave out the where. Update. Set the phone to 555-1212. Okay. Where everything is equal to everything. Okay. And then you've changed every. Updates are kind of dangerous. They're not as bad as delete, but they can be pretty tricky. Because then you find out everyone's got the same phone number in your table. What happened with that? Updating several rows at the same time. Here we go. This is how it happens. Where we update sales, set the price to $4 where the price is larger than $4. Now we've just reduced all prices to $4, essentially. So whatever you can do in the where clause, you can do an update on, essentially. All right, so defining the database themselves, and then we also have this view concept. What time do we have? Okay, we still got a few more minutes. 6:45. Didn't I say 6:45? Yeah, she's going to tell me. Besides, you don't have to torture yourself. You can leave early if you want. Defining a database scheme. All right, so a database scheme comprises of tables, right? So we're declaring the relation of the tables of the database. Many other different kinds of elements can also appear in the database scheme. This is where this becomes very powerful. You can include views, indexes, triggers that we'll talk about. We can actually define them in SQL when we create the database themselves. So how do we create a table? Simplest form, create table, table name. List of elements. So many, and you may remove the relation from a database by saying drop table, space, table name. Drop table doesn't actually remove it completely, as I mentioned before, but drop is the way of, you can't say, well, if you say delete table, you're going to delete all the contents in the table. If you say drop table, you remove the table from the table space area. So it's still saved in a buffer, however. Elements of a table declaration, and this is where people end up getting tripped up. Because depending upon the SQL version and the SQL database you're working with, you have different options. Most of this, 100% of this actually is supported in Oracle. So everything is possible. When you work with smaller databases, you don't necessarily have the same data types. The fields are limited on the data types that you can use for the different fields. You're also limited on how many keys and how you can actually specify the keys. So the principal element is a pair consisting of an attribute and a type. So we list out type, attribute, or attribute type, depending upon what database we're working with. This is the syntax I'm going to show you for Oracle. Integer, int, integer, spelt out. Now I think it's called number. So I believe you can use the word number. It's going to give you a number, whether it be integer or float or double. Depending upon your database, you're going to have different variations within the data types. Here's a classic example, and this works in Oracle. In fact, character, I believe, is being phased out, so var character is what you're going to want to use instead of character, actually. Because it gives you a different length, and it's becoming more standard. In fact, real probably could just put the word number there instead of real. So don't really be concerned with the data types, but look at the format. We have create table cells. Now we're going to create the beers and the bars and the cells. Bar is a character of 20 in length, so we have a 20 character name for the bar. Beer, variable character 20. For all intents and purposes, it's about the same. We can have bigger bar character label numbers of storage if we wanted to. Price is real, or you can put the word number. Interesting thing is the whole thing is in opening and closing brackets with a semicolon at the end. That creates our table for us. No GUI required. 2 seconds, you can create the table, no problem. So we can also put dates and times in the table as well. So the date and times are types. They're date types that we're going to use. And we can specify the form of the date. In the form of the time. This is where most people end up with wrong syntax for the inserts. If you insert a string into a column attribute that's a date, it's not going to like it because it's a string. It has to actually be converted to a date before it can be put into the date attribute column. In fact, there's a data type you actually have to run to change the string to a date when you do the insert. Yes, a question. Oh, I got it coming up. I have it coming up. It's coming up. Oh, your question is different. Wait a minute. Let me see if I can answer your question. Your answer is, it may not be in this lecture set. Your answer is how to get the date in. In the query, when you do the insert, you actually have to use a date function and specify the string inside of the date function for the date that you're setting that you want to update or you want to insert into the attribute. Is that the answer you're looking for? Okay. I know I have an example. I don't know exactly where it is in the slide set, but I know I have one in here because that's a common problem that a lot of people run into in terms of. Now you guys just previewed everything here. I know I'm not gonna finish this today. I know. It's gonna be a 3. It's gonna be a. Well, it usually runs 2 to 3, depending upon how long I lecture for. All right, so dates and times, previously mentioned, we put the attribute, we specify the type as a date. If we specify date, we get the date and the time. And depending upon the database, most of them are pretty standard these days. Time can be in the format of hours, minutes, and seconds. We can actually change it, minutes, hours, whatever. An optional decimal point for fractions and seconds may also follow. Again, the support is going to be dependent upon the database that you're using. Some databases will support minutes, microminutes, whatever. Some may not support more than hours and seconds, minutes, whatever, hours and minutes. So it really depends on what you're working with. That actually causes some problems, especially when you're taking a timestamp. What time did that person place the order? And the time comes in with the date, or the date comes in, and then what ends up happening is you have to figure out, well, what format is it actually in? Because you can specify the format when you create the table. So, declaring keys. You can go. You had that look. Don't worry, if you need to go, go. We only have, how many minutes do we have left? 10 more minutes. Huh? 30. Well, we have 10 to 15 more minutes. Oh, but have us out of here for the remaining people in about 10 minutes. In fact, I'm looking right now for a good stopping point. So be patient. All right, declaring keys. I'm talking to myself. I told myself to be patient. Some of this stuff is just for me to hear. All right, so lo and behold, we can say a primary key or we can say unique. Good transition to talk about primary versus unique. There are different reasons why we want something unique when we're not using it as a primary. A lot of people actually think it's the same thing. It is because a unique key and a primary key are both unique per the row. So, an attribute or a list of attributes may be declared primary key or unique in the SQL create table script. So, I actually call the script in the query. These each say that the attributes so declared functionally determine all the attributes in the relational scheme. It sets the constraint. This is what I call a database constraint. It falls in the category of a well-needed, very valuable constraint that should be set. There are a few distinctions to be mentioned. I'll mention them later, actually, between the two. So where do we place this? We place the primary key or unique after the type in the declaration. So if we have create table beers and we have name character 20 space unique, and unique is the keyword, or we can say primary key. We may not necessarily want to say a primary key on that. Maybe we just want unique ones. So we might be declaring multiple attribute keys as well. So a key declaration can also be another element in the list of elements as well of the create table statement. And this form is essential if the key consists of more than one attribute, multiple attribute keys. We can actually specify that out right here. So now we've created a primary key that's not based on one attribute, it's based on two, and it's based on bar beer. So we have bar and beer together become the primary key. That, for some strange reason, people are afraid to do. 9 times out of 10, when I see a table, I see it on one attribute, no multiple attribute. When if they made it a multiple attribute, then they can actually tell more specifically the unique occurrences. Because, you know, I could have a Barbara Hecker, I could have a Barbara B. Hecker, I could have a misspelling of Barbara, I could have a misspelling here, I could have all sorts of different things, but if I do a combination between social security number and last name or something, or if I don't use the social, or I do something else, maybe I don't want to ask for a social or a student ID or something, I can actually kind of create a key out of the data that exists, when no key here exists. So, yeah. Sure. I'm sorry?
95.
Oh, 95. 95. Here we go.
With this kind of unique, can you create a duplicate name? Because we are trying to say, for example, Smith.
Smith? Well, this is really bad because it should say first name or last name instead of just name. Because
I'm talking about the unique.
On unique, every one in there has to be different in the table.
If you insert another Smith, already a Smith name is there. Insert another Smith.
It won't take it. Because it has to be unique. I mean, you only get one of a kind. So here we have a primary key that's created out of two fields rather than selecting one. We could actually just select one and declare a primary key as well. So we have bar, beer, price, and don't worry about the data types. But the primary key, that's actually works in Oracle, and that's the syntax that you're using for that. So primary key versus unique. The SQL standard that allows you implementers, there's a distinction between primary key and unique, as I mentioned before. An example, some databases might automatically create an index. And the data structure is going to speed up the response, hopefully. We'll talk about indexes. You can actually create an index. What does the index do? It sorts for you. So response to the primary key, but not on the unique key. So it might actually, what ends up happening in Oracle actually is it automatically will create the index for you. If you have a key and it's specified as the primary key, it uses that for the index. So if the index is on a social security number, it's going to put everything in order for you. If you're searching and joining on that primary key, makes it faster, essentially. If you create an index, which you can do on your own, be using a create index command, what ends up happening is every single time you insert a piece of information into the table, the index has to be updated. So here's a classic problem a lot of people do. They populate a table, bunch of data, they create an index on the table, and then they use it for inserts. And they've slowed down the speed of that database significantly. So you index something after you've already populated it with the assumption that you're never going to update it again, and you're going to use it for searching. You're going to run searches on it. That's when you index. And I'll talk a little bit more about indexing as we start looking at the Oracle commands. But that's one of the key pitfalls that usually ends up happening. And maybe you want to say unique, and you don't want to say primary key because you don't want that index created. Because as I said before, unique and primary key are kind of similar in a lot of different ways. They're used for different purposes. They both mean the same thing, but they are treated differently by the database. So depending upon what features are used, and you can't say unique this key and this key. You can't create a composite multi-valued unique key. That doesn't work. When you create primary, you're actually creating a key That's a primary, that you're creating a piece of information outside of, in addition to the contents of that table that you've created, actually. Unique doesn't do that at all. Unique just puts a constraint on the column that says it has to be unique. Can't be a duplicate. So, which means you can only have one of each type. So. Restrictions on the required distinctions. What is this? I think I just went through all this stuff already. So requires, I mean, only have one. Oh yeah, you can only have one primary key for a relation. This is actually good stuff. But several unique values, which is a big difference between the two of them. You can have every column you want unique. That's going to be very restrictive. And the more unique information you require for each one of the attributes, the harder it is to do an update, the harder it is to do an insert on that table. Also, unique won't allow a non-valued attribute, like an empty attribute, to come in. So no attribute of a primary key can ever be null in any row, but attributes declared unique may have nulls and may have several roles with null, because null is neither unique or not unique. Null is empty. So it depends on another constraint you can put on the table, and you can actually write not null, which means it can never be null, or leave it alone and it can be null. If you put that restraint on there, in combination of unique and not null, then you have to put a value in. But if you say unique and leave it so it can be null, then you can have multiple nulls in there. So it's just going to add more null information. What you don't want is the null in the database. You don't want to design a table to use null values, because that adds that third element of true, false, and unknown. It adds the unknown, which can mess up queries. So other declarations for attributes, as I mentioned, and I think this is probably a good stopping point actually after this, because this makes sure, yeah, after the example. We have not null means that the value for the attribute can never be null, as I mentioned before. The default, let's say you want to put something in by default. Yes? Say one more second.
Something which is taken automatically by default?
Yeah, it's taken automatically. I have a slide. Actually, the next query is going to show you. Is that your question? You can use them both together. You can use default on everything. You can put default on every one of your columns attributes. Unique and default aren't going to work together. Because if you think of the concept, if you have a default value, it's never going to be unique if the field is left empty. In that case, you want to make it null. You don't want to use default. And here's your example where we have create table drinker, name as a primary key, address, default 123 Sesame Street, because we don't want an empty address. So we can query and say, well, what is his address? 123 and Sesame Street? Oh yeah, he didn't give us his address. You see this a lot when people filling out forms. Here's what happens when you do form checking galore. So every form is filled out correctly. Yeah, but lo and behold, something gets through the system, and the query, the update happens, the insert happens, and then what? Nothing is coming through for that particular field. It's empty for some reason. It got translated incorrectly. So you put a default value in there, and then occasionally you do a search, you do a query on the table for the default value, and you go, how many of these 123 Sesame Streets do we have? And then we call a person up and say, hey, what is your address? It's not right. Or sometimes it says, not provided, unknown. So different words can be put in there, or, to fill in the blanks, essentially. And the effects of defaults, suppose we insert the fact that Sally is a drinker, but we don't know whether or not the address, or whether or not she hasn't given us an address, or she hasn't given us a phone number. And insert with a partial list of attributes makes the insertion possible. So we have insert into drinker's name. And everything else we're going to use the default values for, essentially. And here we have 123 Sesame Street that's being put in as the address. So. But what row appears in drinker? Well, that one does. So that's the row that appears. So if we had declared a phone as not null, that insert would have been rejected. So what ends up happening normally is if we put in not null and use that, that helps us ensure the integrity of the database. going back to my comment on constraints, the tougher we make it to get information into that database, the more valuable the information is overall, because we have good information. If we open it all up, don't use unique, don't use primary key, you know, make everything null if possible, then we can have an entire table full of nulls. Doesn't really tell us very much about the information in the table. In fact, it's useless, actually. And it runs slowly because it's not indexed, because there's no primary key. All right, I will stop at this point, because I know I'm close. I'm not reminded yet, but I'm close. All right, so next time we'll go over part 3 of the SQL Bootcamp. And then after SQL, we work on entity relationship diagramming. So I'll come up after. I'll come up now. Yeah, come up over here. Yeah, it's easier because I can't yell that far back. And you may not even hear me back there. All right, see you next time.